Girdisi? Nesigirdi, ne? Tai ar girdite? Taip neblogai, jo? Svarbiausia, kad užpakalinės eilės girdėtų. Tai, kad čia priekį dedasi, tai gal.
Girdėtų priekį. Kas galėtum nerūpė.
Tai ką? Tai važiuojam.
Okay, good afternoon, everyone. I'm Mangirdas Malinauskas from Laser Research Center of Vilnius University, and it's great to see lots of you gathered here to listen to Professor Andrius Baltuška, who actually is a physicist from Vilnius University, graduated in 1993, right? And when he moved to do his PhD work in year 2000, he completed it in a group of Professor Diderik Wiersma. Later on moved to Japan for a couple of years to work in Kobayashi's laboratory in University of Tokyo. Afterwards, he returned back to Europe, to Austria, to work in Professor Kraut's group. Also moved in Max Planck University Institute, and later on, since 2006, he was assigned as a young group professor in Technical University of Vienna. So about his topics or research topics, he will talk on your own, yes, but one or few details to mention.
You can go on. Okay,
No. The text is short. So it's good to know you are a world record owner, right? We were taught in master studies that you are, or you were at that time, holding 4.5 femtosecond light pulse.
Okay.
What year was it? It was 2000. It was announced as 2006 for
Let's
us.
say the record was beaten many times, and sometimes we're back on top, sometimes somebody else is there. So
Olympic competition, yeah?
It doesn't count.
Okay, thank you. So you have 50 minutes to present.
Thank you very much. It's great to be back. So I knew this place as a forest. I still see some leftovers of the forest around, but I really had a difficulty finding a place. So it's good to be in the modern age. Google knows it, Uber drives you. And I'm delighted to be here. I'm delighted to share with you some of the hot topics that are going on in our lab at the Technical University of Vienna. And I was warned to be, let's say, sufficiently pedagogical, such that also people with bachelor background can follow what I'm saying. So I tried to structure the talk as simple as possible. And essentially, I want to tell you a story from the point of view of the electron, which is freed by the electric field of the optical pulse. So we will see that to be freed, this electric field has to be strong, so to break to overcome the forces that are connecting the electron to the atom. And also, the main emphasis of that will be that the events that we're talking about, essentially they're born on a time scale of a fraction of an optical cycle. So of course, after that, there's like almost an endless scenario. What could go on after that? But it all begins in a very short, at the second time window. And a little bit later, I will give you some time scales and talk also about the spatial scales. Now, I really don't know how to optimize the presentation. So is it okay that I point at the screen rather than control the mouse? Yeah, so let's say we'll stick to that mode. And if you get lost at any point during my talk, you just need to sort of mentally go back to the slide. So here I just tried to represent the story in the most succinct way. If I, say, didn't have the wonderful means of PowerPoint, I simply had to tell you the story using one single image. So the image is that we have matter, so we have electrons sitting somewhere in the potential well. Then the electric field comes in the shape of a very short laser pulse. So of course it's an electromagnetic field. It has not only the electric field, but also the magnetic field component, but I will deliberately not talk about that. It's a all separate paradigm what the Lorentz force can do. And what counts here is that we will liberate the electron. And the rest of the story will be what we can do with those electronic wave packets. And just as a sort of helpful way of visualizing it, the easiest thing to observe would be a spectral change of light. And when we come in with light at the frequency omega naught, so that's the carrier frequency, the observable that we can monitor the easiest would be the repeated images or the harmonics of the same spectrum. So I guess that everybody understands, regardless of the background, whether it's optical background, general physics, or even probably high school is sufficient. Now, before I plunged into all of that, of course, I would like to say a few words about the place that I work in, and it's a delightful little city of Vienna. So very famous for its cultural attractions. So we're located here. The green buildings, they indicate the properties of the Technical University of Vienna. Recently, 2 years ago, it celebrated its 200th birthday. So that's the central administration building. Looks like this, looks wonderful. Erected on the place of a former cemetery. And we have world-famous culture heritage points just next to us. And I guess it's enough to mention that the opera is just across the square. So it's like 300 meters away from our central building and like 600 meters away from where we are. And another very famous building is probably every year on the 1st of January, you see this wonderful New Year concert from the Musikverein in Vienna. So this is also just several hundred meters away. So to put this long story short, we have lots and lots of visitors who simply enjoy being in the wonderful city of Vienna. And it's also one of the hottest destinations for conferences. That's a zoom at our main administrative building. And I'm doing it for the sake of showing you this. That's my most favorite feature of our university. On the side wall, there's a memorial plaque commemorating the two famous composers, Johann and Joseph Strauss. And the inscription says that before they became world famous musicians, they actually studied at this Royal and Imperial Technical Institute. And it always inspires me to think that, well, if you fail in technology and science, there's always life after that. So you can go and do maybe a musical career. Now, a few words specifically about what we're doing. Our group is built, or rather, consists of two main thrusts. One of them is led by one senior scientist, Markus Kitzler. So he leads a team that works on coincidence momentum imaging of the wave packets that I will be talking about, and on attosecond spectroscopy. So essentially using the X-ray light that we produce by means of accelerating those wave packets. I will say a few words about his work. So the second thrust in our group is led by Audrius Pugždys. So he's very famous, very familiar to, I guess, many older generation people here. And so under his supervision, we run laser development and more conventional nonlinear optical spectroscopy. So here I'll just demonstrate the typical way of repairing lasers in Vienna. Now, I was tempted to put many thanks to our group members, but I'm really scared of leaving out somebody, so I just thank them verbally. And if you want to see who represents our group or has represented it over the years, you can visit our website. Just would like to say a few words about our key cooperations. So we cooperate steadily and for many years with many groups, theoreticians and experimentalists, and some of our most important partners are the groups led by Professor Baltuška. So he has many affiliations. He is with the Russian Quantum Center near Moscow at the Moscow State University, and he also has an equally important group at the Texas A&M University in College Station. So we also have very strong ties to geoionist groups in Colorado. So I will say a few words today about our collaboration with INRS Canada, with our most recent experiments with the University of Maryland, so that's Professor Howard Minchberg, and lots and lots of other cooperations that I will just quickly refer to as we progress. Now, very importantly, so the technology that we use, ultra-short laser pulse technology, and specifically the tunable wavelengths laser pulses, we owed entirely to this place and to the efforts of Professor Piskarskas. And other colleagues, some of them I've already seen here, so it's once again good to be back, good to see your faces. And I just want to say why this technology is so important. Because as you will see, one of the key aspects of what people are doing nowadays in strong field physics is the use of long wavelengths, or at least the wavelengths that one cannot get directly from lasers, because such laser materials simply don't exist. Mother Nature has not supplied them. And back 30 years ago, it probably looked like more like a child play, like a thought experiment. So Professor Piskarskas pioneered one very wonderful idea. He first tested what happens when one amplifies short pulses in an optical parametric amplifier. And this work was published in 1986. So those of you who are more intimately familiar with laser physics know that we sort of benchmark the year 1985 as the sort of turn of the technology, because that year the most famous laser technology that delivers intense pulses was realized. That was the effort by Gerard Moreau and Donna Strickland, and they termed the invention short pulse amplification. So that was using laser medium. So Professor Piskarskas pioneered a special case of that. I guess the battery is it still okay? Or is the sound not very stable? Okay. So I think it really depends on how I turn my face. So if, please let me know if I get carried away, so please stop me. Right. So what the group of Piskarskas did, they amplified short pulses, and that was pretty much in the same year as short pulse amplification of laser pulses was done. So this idea had its continuation in 1992. That was the first pioneering paper on the so-called optical parametric short pulse amplification. And I was very fortunate to be a student during those days. Like I said, I graduated in 1992. And the main person on the paper is Audrius Dubietis. And he works with a twinkle laser. It's a laser, it's not an OPA, but we couldn't find a photo where he would be working with an OPA. So the photo is from 1992. So once again, that's the key technology that enables us to do things that we do. And it has two merits. It allows you to choose different wavelengths from what you get directly from the laser. It also allows you to generate very intense and very short pulses directly. And a little bit of a motivation about what I want to talk about in this talk is the time scales, the space scales. So of course, we all know that the planetary model of an atom is a very crude approximation because electrons are not really hard balls flying like planets in the solar system. But the model is good enough to explain the main features or the main constants or the Bohr in the Bohr model of a hydrogen atom. So the first orbit has an orbit in time of 152 attoseconds, and 1 attosecond is 10 to the minus 18 seconds. Or it's 1,000 times shorter than a femtosecond. A femtosecond is 10 to the minus 15. And one also has corresponding spatial scales. So one optical cycle at the wavelengths of 700 nanometers is 2.7 femtoseconds. It's a good number to remember. And correspondingly, the spatial scale is sub-micron. And what people do routinely now, you can even buy it commercially, is systems that produce isolated attosecond pulses. And typically, they all end up around 100 eV or around the wavelengths of above 13 nanometers. If I have the time, I will say a little bit more later about the importance of the spatial scales. But at the moment, I want to stay on the temporal scale. And that's a wonderful slide from Rick Tribina, where he simply put all the prefixes on one slide. And you can see what people can do nowadays. So they're somewhere on the order of 50 to 70 attoseconds. It's 1 quintillionth of a second. And sort of to warm up, to move to the subject itself, what we're dealing with is non-perturbative optical field and matter interaction. And it could be sort of visualized or animated like this. So this is the potential well, and we have the electrons sitting deep within this potential well. So when we're applying an external electric field, we induce polarization, and this polarization, sorry, went too fast. So this polarization reproduces the driving electric field with a very high fidelity. So it's a linear process. So that's how we treat linear interactions. Then when we talk about nonlinear optics, we still talk about bound state electrons. But what happens now, we feel the unharmonicity of the potentials, and therefore the polarization that we induce, it no longer faithfully reproduces the driving field. So if we now perform a Taylor expansion of this signal, we would get harmonic terms. And that's how nonlinear susceptibilities are introduced. And it's essentially all our science about nonlinear optics is a Taylor expansion of the nonlinear response to a driving field. But once again, what counts is that we're talking here about the bound electrons. And by contrast, what we want to investigate here is polarization for very intense driving fields. And the key feature is that the electrons completely leave the atom. And so I schematically visualize the signal. It's extremely nonlinear, but we can even look at it from a different perspective. What we're doing, we're generating plasma. And this plasma oscillation also works as a source of radiation. So that applies everywhere in technology, from any radio transmitter, so it's a dipole oscillation, and it also applies in optics. And I will specifically talk about different types of optical and terahertz and X-ray radiation that could be produced by this method. So the key moment is the liberation of the electron. And the scientist who is credited the most for the advancement in this field is academician Keldysh. So he passed away 2 years ago. And he wrote a seminal paper in 1965. He was dealing with semiconductors. And after that, he moved on, and for decades he was active in a completely different area, while everyone else was reading and citing his paper all the time. And I don't even know how many times the paper has been cited. So essentially, what he noted is that there is a transition between an oscillating behavior and a DC field impact on a potential well. So when you apply an electric field, it distorts the potential. If it distorts it so strongly that the electron level opens up, so the electron just travels out. So this is called over-barrier ionization. And if it bends it and it keeps it for a fraction of time in this position, so one creates a barrier through which one can tunnel. So this is called tunnel ionization or tunneling ionization. And people are still arguing, and they're trying to make their point about the difference between multi-photon ionization and tunneling ionization. So multi-photon ionization being the addition of the energy of multiple photons that kicks out the electron. So essentially, it would work the same way as or similar way as a single photon ionization, where the energy of a single photon is large enough to put the electron from the bound state into the continuum. So the point is that the terminology is a little bit creepy and very unsuccessful because, of course, both processes are multi-photon. And there are different names being used throughout the literature, like optical field ionization and things like that, which are probably more useful, but they in turn also create a confusion. Now, depending on your intensity, depending on the electric field, so the intensity of the pulse and the driving frequency, one differentiates between the two regimes when you're multi-photon, when you're tunnel ionizing. And what else you see in this formula is the effective mass of the electron and the binding potential. So all my story will be about that. And if you lose me in one segment, then I hope you will be able to tune in again when I switch to the next segment. So I want to start with a very simple reasoning that we're applying our strong electric field, and we have ionization events. Of course, ionization events will be stronger at the field peaks of the optical pulse. So that immediately gives you a suggestion that, first of all, the outcome of the interaction would depend on the so-called carrier envelope phase. So this is the exact shape of the field oscillations under the envelope. If the envelope is short, so the number of strong cycles will be very significantly limited. If you are dealing with a single cycle pulse, you will only have 1 or 2 strong half cycles, and that will change the whole game. And the ionization probability very, very nonlinearly depends on the intensity. And you see that a small increase in the peak intensity corresponds to the strong adjustment of the yield. So the yield is shown here as a dashed line, and the electric field of the pulse as a continuous line. And once again, what I did not talk about here, and I will not talk, is the magnetic component of the electromagnetic field. So as the field passes, so it bends the potential to the left and to the right. So therefore, with the next half cycle, so the story will repeat itself, and it will repeat itself again. And this essentially gives rise to lots and lots of observables that we can detect, lots of processes. We will talk about the process of high harmonic generation, or HHG. And there are weird types of ionization. So when you come back, you recollide, and you kick out another electron, so non-sequential double ionization. And a very interesting mechanism of above threshold ionization. So I would like to talk about that for maybe like a minute, because if you understand that part, you will also very easily understand optical harmonics. So what you do in ATI, above threshold ionization, you look at the photoelectrons. And what those photoelectrons can do, of course, once they're released by one of the peaks of the electric fields, they continue sort of interacting with the field, and their momentum is constantly being changed. So they're accelerated, decelerated, accelerated again. And if you use linear polarization, that means that you are staying sort of in the plane of the electric field polarization, and you may come closer and back again from the parent ion, and you experience the so-called rescattering. How to understand rescattering? It's a little bit like what people do in space technology. If they want to accelerate a spaceship, they actually use planetary forces to turn it around, give it a more push, and the same happens here. And this rescattering can happen up to 3 times, and the so-called maximum electrokinetic energy can reach the value of 10 ponderomotive potentials. Ponderomotive potential being described by the field strengths and the optical frequency of the laser pulse. Another way of saying is a quiver motion supplied by the electric pulse. So this is very interesting, because what we can do, we can directly collect those electrons with the spectrometer and just map their kinetic energy. And the spectra would consist of peaks, which are very similar to optical harmonic peaks, just that they are represented by kinetic energy. And just jumping one step ahead, it's a one-to-one situation, correspondence to what we have in the high order harmonic generation, the difference being that we exchange the kinetic energy of the electron for the photon energy, which is being released by the parent ion. Okay, now to sort of connect it a little bit to real-world technology, there's a famous invention made by Gerhard Paulus. So at the turn of the century, he combined two spectrometers, to the left and to the right. So both of them are detecting photoelectrons. And he sends a short pulse through a target. So the target has a gas jet with gases like xenon, and records the spectrum. And what was shown is that depending on the shape of the pulse, so the highest kinetic energy of the electrons lies to one side or to another side. So it lies to the side where one has the strongest electric field peak. Actually the opposite, because it's electron has a negative charge. And this technique became super famous. People have developed it into the so-called, colloquially known as a potato meter, a device that allows you to characterize the carrier envelope phase of a short pulse. And so those data were taken in the Vienna lab. And now this is a more recent application of this technique. So Tadas Baltuška became very, very famous for several experiments that he has done during his PhD, and one of them was self-compression of high-energy pulses, or high-intensity pulses, in a so-called kagome fiber. And he compressed them so much that they became shorter than the optical cycle. So what is important here is that the wavelengths of this pulse is 1.7 micrometers. So this is much less than, or not much less, it's less than an optical cycle. Therefore, such a pulse cannot freely propagate in open space. And that's the application of this technique, where you see that the highest kinetic energies of the photoelectrons are very different to one side and to another side. And from the ratio of those energies, one can also retrieve the temporal shape of the pulse. Now, essentially, I could summarize all ideas in this slide. So what we do, we release an electron by one type of ionization or another. So if we use tunnel ionization, we love it because we have a perfect temporal synchronization within a very short attosecond window. And we will talk about high harmonics, which is a process running on its own. So this is the rescattering of the electrons, the return to the parent atom. There's a famous technique which uses both ionization, but this is a single photon ionization with an XUV pulse, and the temporal mapping of the position of the photo electron, or rather the momentum of the photoelectron. So the freed electron changes its momentum as a function of the remaining electric field of the pulse. So you know that the Gauss theorem says that if you close the electric field over the source or over a pulse, it should be zero. What we do, we break this condition because the electron appears at some point within the pulse, and therefore we're integrating not over the whole enclosed field that leads to zero, but over the remaining part of the field, and that will result in the final kinetic energy that the electron would still have after the pulse. So this is the main idea of streaking, which is nowadays applied to gases as well as solid-state media. And yet another class of events is when you start manipulating the electric field of your driving pulse, for example, by adding colors to it. The easiest combination of such type is the so-called two-color combination of omega and 2 omega, where you simply mix the second harmonic of the fundamental frequency. This is very easy to do, and on top of that, it's phase stable. And then this is the whole host of processes that can be triggered by that. So probably the most famous type is the generation of very high terahertz, high intensity, high electric field terahertz fields, pulses, which is exactly the manifestation of this oscillating plasma. So what we do, we leave the plasma, and the kinetic energy of the electrons in this plasma, it's not zero, just because we break the symmetry of the optical cycles. And I will mention a few more examples. Okay, so I'll skip the colorful patches. So one thing which is also coming from the work of Tadas Balčiūnas, he sort of further developed the famous technique which was pioneered by Hochstrasser. So that's what I already alluded to. You take the fundamental and you generate the inline the second harmonic. So the field symmetry is broken, and that releases a component which is similar to optical rectification. So it corresponds to terahertz radiation at very, very low frequencies. So now if you take optical frequencies which are not exactly have the ratio other than 2 to 1, so we call them incommensurate, because it's not an not an integer number, the frequency ratio. You can actually tune the optical frequency of the terahertz. And that was very important breakthrough, because one had to do quite a lot for the laser technology. First, one had to understand how to make both pulses phase stable, or at least keep the relative phase of the pulses locked to each other. As a result, you obtain something similar to a tunable OPA, except that here you tune the frequency of the terahertz light. Now, another manifestation of plasma. So as I said, the easiest thing for us to monitor would be the spectral components, and those spectral components would be the harmonics of the driving optical frequency. So the thing which is most well known nowadays in the strong field physics is high order harmonic generation. So credited to Paul Corkum, who was the first to explain it in 1993. And the following year, a paper by Kullander and co. Came that gave a also quantum mechanical explanation of that. And we will talk about that a little bit in more detail in a couple of minutes. So, but before that, I would like to draw attention to low order harmonics. So the lowest orders, probably most of you are familiar with that. So even, I suppose, this green line of the pointer is the result of the frequency doubling. One is a nonlinear medium that has one or another type of nonlinear optical susceptibility. So this is what we call perturbative regime of nonlinear optics. Once again, as I was showing in the beginning, it refers to the bound states of electrons. And another very interesting type, which is sometimes remembered, sometimes gets forgotten again, is the oscillation of exactly this plasma that we create by ionization. It was explained by Francois Brunel. Actually, it's a couple of years before the harmonics were explained in a different way by Paul Corkum. And there's also no surprise, because Francois Brunel and Paul Corkum, they were roommates in the same office. So now this effect has a very interesting origin. So it exactly can be exactly explained by this emission of electrons into the continuum. So what you see here is the instantaneous intensity, which is just electric field squared of the driving pulse, is shown in red. Then in blue, it shows the ionization yield. And as I argued before, it has a much steeper dependence on intensity. It's exponential, so therefore it's only confined to several optical cycles. And now what is important is that every optical cycle carries two half cycles, and therefore the effective frequency that we're dealing with here is 2 omega, omega being the carrier frequency of the pulse. So that means that twice per optical cycle, we have a ejection of electrons into the continuum, so the frequency 2 omega. And what it does, it changes the refractive index of the medium. So one word of caution, if there are serious theoreticians here, they could attack me about the definition of the refractive index. And they would be absolutely right, because one cannot define a refractive index on something less than a completed optical cycle. So it's a little bit of a jargon that I'm using here. Nevertheless, one can argue in a very simple way. What you're doing, you're emitting plasma in kind of stepwise manner, and that changes propagation conditions for the optical pulse. And I will just progress onto this slide. This is a sort of what I call the toolbox of optical sensing, and it could be understood in terms of interaction with an amplitude mask and the phase mask. So amplitude mask would be the loss of the change of amplitude, for example, because of absorption, reflection, scattering, and phase mask is because the local speed of light changes on the short temporal scale. And for media steady state case, so no absorption, no phase change in time, we would simply preserve the spectrum. It's an invariant of the optical propagation. So if we do have a tunneling event that changes the plasma density twice per optical cycle, we will create a phase mask like this, which will contain those steps. And there's also an amplitude mask, but it's less important, because even if there were no phase amplitude mask, the phase mask alone would correspond to the generation of new frequencies. So if the process is smooth, like generally accepted for multi-photon ionization, then it would simply result in the blue shift of the transmitted spectrum, which is very well known from plasma physics. And this is due to the fact that the refractive index change would be a derivative proportional to the derivative of the envelope, or of the yield, actually. And it would, because of the laws of Fourier transformation, it would correspond to a frequency shift. And since the density increases, that would correspond to the blue shift. And the limiting case would be ionization with a single photon, but this photon has to have the energy sufficient to kick the electron out into the continuum. So that would be like an abrupt, very abrupt phase mask, and that would correspond to the generation of an extremely broad spectrum. So that was like optical talk. And in fact, one can also redraw it in terms of radio physics, so everybody understands the principle of a frequency modulated radio. Essentially, modulation of the phase leads to the appearance of new frequency components. And any parametric process, including the second harmonic generation and optical parametric amplification, also can be understood as a way of modulation of the electric permittivity. So here we modulated at the frequency of 2 omega pump. That's because I said we have twice per optical cycle emission. I guess I need to triple the speed to get somewhere. So what I was talking about here is the ability to detect essentially this at-the-second behavior by simply observing harmonic spectra. So that represents Fourier transform inverse Fourier transform. And we've done some work to prove it in gases and solids. That's already a while back. You see that the observables are those generated harmonics. And now the whole thing kind of gains new sense. We were looking at it back then because we wanted to understand what actually causes material damage, whether it's due to impurity levels, even in the cleanest optical materials, or is it due to tunneling across the band gap. But now people have taken it further, and I recommend that those of you interested take a look at the current activities of the Ferenc Krauss group, so my former boss in Garching, and in Vienna as well. So they're talking about transient metallization. So this is the ability to turn a very robust dielectric into a conductor, which gives hope of creating petahertz electronics, because the optical frequencies in the petahertz range, and we're talking about modulation twice per optical cycle. And they have brought it even further. They're doing biomedical sampling by monitoring the transmitted waveforms. Okay. I want to spend a few minutes talking about the most important technology. It's high-order harmonic generation. That's probably the most known topic for high-intensity tabletop lasers. And the key features are that the emitted harmonic light retains spatial and temporal coherence, and therefore what you obtain is a laser-like beam, even though the mechanism of generation is, of course, far from being a laser mechanism. And here comes this promised explanation by Paul Corkum, who what is nowadays known as a three-step model. It's a paper, I don't know how many times it's cited. It's probably well over 2,000 or 3,000 times. So this is an unperturbed state, and that's the bent potential in the electric field. So the electron is released, then it's accelerated, then at the turning point, it stops and starts getting accelerated back toward the potential. And then with a tiny probability, it may recombine with the parent ion. Now, unfortunately, this probability is really very tiny. And the longer the electron spends in the continuum, the smaller this probability becomes. And therefore, there's this one very significant nuisance that if you use a longer wavelength, longer lambda light, the probability will keep going down and down. So one of the reasons for that is called quantum diffusion, because it's not an electron flying out as a hard ball, it's a wave packet, and the wave packet spreads. So therefore, the cross-section or the overlap becomes smaller and smaller. But there are also good things. So for example, if you scale the wavelengths, you can do it with a less intense laser. And doing it with a less intense laser frequently means that you can solve lots of other problems, for example, like the density of the neutral gas and things like that. So I will show you a couple of examples, and I hope I will still have the time to do that. So essentially, what we're talking here is a process that combines the energy of many driving photons into the photon energy of one XUV photon. So that's the kinetic energy of the returning electron, which is exchanged into the energy of the emitted photon, and the electron becomes bound again. And here's a significant difference between the process of HHG and ATI. So above threshold ionization that I talked about before. When we talk about ATI electrons, they simply fly away. We can capture them on the detector. But here we need to return the electron or electron wave packet almost the same way as we need to retrieve a spacecraft that has to land back on the planet and not to fly, not to miss it. Yeah, so the interesting point is this pre-factor 3.17. Historically, people sniggered at it and they said that one famous scientist even argued that he made a bet for a bottle of champagne, I guess, that it would be a factor pi, but it's not factor pi. And the reason for that is that when you generate harmonics, you need to fulfill several conditions. And okay, one of the conditions is that the electrons have to be recovered, so they have to get back to the ion. And fortunately for us, we can treat those electrons as quasi-free particles. And the solution of this Newtonian equation of motion actually gives you this factor 3.17. So now, just in 10 seconds, I'll try explaining a few things. We're doing things twice per optical cycle. So the electrons are born at the peaks of the electric field. If they're born exactly at the very peak, this is the highest amount of electrons going out, but we're not able to recover them because they don't correspond to returning trajectories. So returning trajectories are of two types, the so-called short and the long ones. And let's say they do generate harmonics, but we need to understand the following. Can those individual harmonic lines be phased together to represent the short pulse? Or do they have chaotic phases more or less like white light, and therefore they will not correspond to a short pulse? So this situation, a column of attosecond pulses versus this situation, a chaotic noise. And that was proven already at the end of last century, that in fact they are locked to each other the same way as modes are locked in a mode-locked laser. So fortunately, nature has done this mode locking for us. And people talk about two types of chirp. One is the chirp of each individual harmonic, and another one is the phase excursion or phase difference between neighboring harmonics. So this is, of course, more important for forming the attosecond structure. So this is called the attosecond chirp. Okay, so this is basic theory. If you're interested, you can maybe ask me later. So one important thing to notice, if you use very short pulses, at the edge of your harmonic spectrum, you only have one or two bursts of radiation depending on how your phase looks like. So, and that describes the features seen in the harmonic spectrum. So here you see the spectrum, photon energies. Here you see the intensity of the harmonics. Here you see the driving field shown in red, and those are electron energies which are then exchanged into the photon energies. And you would notice that this highest energy, photon energy, corresponds to just one half-cycle interaction. And on the left, you see this another explanation of the three-step model by Corkum. So what it tells you is that if you use a very short pulse, you will get a single attosecond burst. And another point is that if you use spectral filtering in the so-called cutoff, you will get an isolated pulse. And that's essentially the base type of the technology which became available back 50 years ago when we managed to phase stabilize the laser amplifier. So the technique existed before, but we could not generate pulses reliably because the phase fluctuated. Okay, and now I want to show you more recent implications of that. Before I want to link the two scales. So spectroscopists frequently talk in nanometers. People in technology also talk in nanometers. You might have heard all this talk about 13 nanometer EUV extreme ultraviolet sources for lithography that currently defines what we can have in our mobile phone technology and the computers. Samsung has already produced memory chips based on the 10 nanometer process. So the light used there is incoherent light produced in many different ways. Now, for 13 nanometer sources, people use CO2 lasers that explode tin bombs, and they use fluorescence of tin to generate this incoherent light at 13 something nanometers. So the keyword is incoherent because otherwise, if you have coherent light, you would have unwanted diffraction, and you would screw up the patterns that you want to produce by lithography. However, what you want to use for metrology is exactly the opposite. You would like to use laser-like beams, and it would be ideal if the wavelengths that they deliver would be shorter than the size of the features that you are monitoring. And 13 nanometer technology corresponds to this. So to the electron volt number 100 electron volt, so which is roughly also where the K absorption age of silicon sits. And that's what you typically can achieve with an 800 nanometer laser. So if you go beyond that, if you crank up the intensity, you will get high energy photons, but there will be very few such photons, and one needs to solve another very big problem, how to do phase matching. So one thing that we already know is that you can manipulate the intensity, you can also manipulate the wavelength. And if you bear with me, I want to show two approaches here. One of them is exactly changing the wavelength. So instead of taking the laser wavelengths, we would take an OPA, and we would divide up this energy into the energy of two parametric waves, signal and the idler. So that corresponds to shift in the carrier frequency down. That creates a longer optical cycle and therefore a longer time over which the electron can accelerate. And that brings the following advantages. So this is a comparison of traditional titanium sapphire lasers with the lasers, for example, used by us at the wavelengths of 4 micrometers or 4,000 nanometers. So if you fix the intensity and you only look at the wavelength scaling, you would have the gain in the kinetic energy of the electron by a factor of 25 because the wavelengths differs by a factor of 5. Yeah, and we like exploiting such differences, and we like building sources of that nature. So I need to ask a question now. I've talked for 55 minutes, and can I use another 10?
You can use the coffee break if everyone agrees.
Okay, good.
If we're interested, yeah.
Okay, I'll just mention significant points. So we need to be aware of two things. One is the cutoff energy, photon energy, how far you can push it. Another one is the so-called phase matching cutoff, because we need to phase together the individual processes occurring on each atom. And this is done by manipulating gas pressure. So the technique was developed by the group of at Gila, Margaret Monan and Henry Kaptein. Some very famous papers came out of that, and they brought this technology to our lab. So the points tested here, the wavelengths of 4 micron, they are done in Vienna, and they confirmed that you can have both. You can have the cutoff scaling and the so-called phase matching cutoff scaling. So this remains to date the world record in terms of the supercontinuum generated. It consists of many, many harmonics. There are more than 5,000 of them. You cannot resolve individual ones. And it comes in a laser-like beam and behaves like a coherent beam. So I'll show the photograph of the diffraction experiment. And if it would be possible to phase all components together, it would correspond to a single attosecond pulse. So of course, this is just a dream at the moment. So what would it be good for? One can do a lot of metrology with it because it covers all the important transitions of metals, so absorption ages, especially relevant to magnetic research, so magnetic so-called L absorption ages. Other ages like M ages, N ages, they're less interesting, but at least they're accessible with smaller tabletop lasers. And another thing that everybody's dreaming about is doing high resolution and also time-resolved microscopy. So for that, you need to be within this so-called water window between the absorption ages of carbon, which is 286 approximately electron volts, and approximately 532 the absorption of oxygen. So this is called water window. You can look at biological targets. So, and the main challenge here, the principles have been shown. So we need to increase the flux. And another approach is instead of playing with the wavelengths, we can construct different types of trajectories, and this is done in cooperation with the group of John Morangas at Imperial College London. So they generated this, sorry, I'm jumping ahead of myself. Instead of just taking one wavelength out of the OPA, we want to take three, and we need to learn how to phase them together. And then you have a very complicated waveform. But this waveform, and here's the idea proposed by John Morangas, can be used to optimize three things. It can be used to optimize the burst of the electron wave packet, the acceleration, that you have a very sharp acceleration point, and you keep the rather interval, and you keep the whole process very short so that you don't allow quantum diffusion to play an important role. And also you need to solve the problem of landing the object back on the planet. So this is all done by manipulating several Fourier components. And in our particular implementation, we use the wavelengths from the OPA and achieve the following. So we have pulses that come like 6 times less frequently. That's because the beat form created by those 3 waves is much longer than that created by one fundamental frequency. And that corresponds to a much denser spectrum and also a much higher energy of those individual pulses. So if you want to follow up on that, that's the paper. So that's a totally different approach. So instead of relying on this sinusoidal wave trajectory that results in 3.17, we need to do, we can design our own trajectory. And now, maybe I'll have to stop after that. So we want to be more and more relevant to applied research. And of course, the dream would be to do time-resolved diffraction. So this is the first experiment which was done with this kilo-electron volt continuum back several years ago. So we just set filters that transmit sub-nanometer wavelengths and slightly above 1 nanometer through a classic Young's double slit, and recorded the patterns. The problem was that it takes a long time because the photon flux is low. And we've been working in the recent years on solving several problems. And one of them was building optimized lasers. So for that, we went back to the wavelengths of just 1 micron to take it straight out of the laser. We compressed it to about 20 femtoseconds. And we were able to profit from this lambda scaling and the direct accessibility of the laser light at the fundamental frequency. So far, we are targeting different wavelengths, not 1 nanometer, but rather 7 nanometers. And the results are very good. So this is a cooperation with a group of François Legaret from OLS in Montreal in Canada, and also the corresponding institute. And what we have achieved is the time-resolved diffraction imaging. So the diffraction is caused by the self-organized magnetic patterns on a transmission probe. And we measure the intensity of this diffraction. So this is this first so-called pump probe result at the wavelengths of 7 nanometers. The machine looks like this. And the important part is as follows. This has to work at a low repetition rate. Low repetition rate here being 500 hertz, because you need to excite on the probe. So if the experiment would only depend on the X-ray flux, you can simply use a megahertz laser and generate lots of XUV photons, and some people do it. But if you want to do time-resolved measurements, you need to excite and probe, and you would simply burn a freestanding sample by the optical light. And we found it really a great surprise. We optimized the laser to work at 2 kilohertz. In the end, we only worked at 500 hertz. But at least we're the first in the world to use this advantage. Okay. I guess in order to let you drink some coffee, I need to stop here, which is roughly the middle of what I wanted to say. So, but I cannot abuse the hospitality.
Okay, thank you for understanding. Thank you. And if we still have some questions for perhaps the mysterious second part, we can ask them in advance, please.
I'll ask a question, or maybe ask for a comment and a real question about the first part. So, in your depictions of what happens to the electron in this potential, you were sort of having trouble distinguishing between different types of ionization. So either it's tunneling or multiphoton or both. And I think my sort of perception of this was that you were sort of sometimes operating in electric field mode and sometimes switching to the quantum picture, so to, let's say, photon mode. So, I mean, tunnel ionization you can probably have in DC field, whereas multiphoton would be difficult because photon energy there is 0. So that's just a comment. But I wondered if you could actually make the energy of your harmonics higher somehow, that's just an idea for an idea, by accelerating the nuclei, so the protons, for example, if we talk in hydrogen atom picture. So suppose you inject from a sort of proton gun, like multi-kilo electron volt protons, with which your electrons can then recombine in sort of head-on collisions. Would that be a way of getting higher energy photons?
Higher energy photon, you're talking about photon energies, not about...
So shifting towards
okay.
X-rays.
So Mark, there was no connection between us before the talk, so, but now that you forced me.
Oh, I'm sorry, guys.
Let me talk about the photon. So what I was describing is this driving by the electric field where the wave function, okay, now let's use the wave function picture. So the wave function that has left the atom is returning back and recombines with the remaining part of the wave function. But, as I said, you can also treat it in a semi-classical way that you had an electron, you brutally ripped it off, and now you can land it somewhere else. And this is also done, and that would immediately bring us into the hard X-rays. And the experiment like this would look shown here. So you excite a foil. After that, you need to shift the foil because you blow a hole there, but it's cheap. It's more like a tape recorder. And what happens is that this poor electron goes out. Okay, I don't have a schematic, but it goes out. It's just that it returns to a different atom. So it does pick up high kinetic energy. As I said, we can treat it almost entirely classically. Yeah, it's just a hard ball, and it just sticks back into the foil, gives this energy to a totally strange atom, emits a photon. The only problem is that this incoherent emission. So, but the beauty is that it would correspond to lines. So for example, K alpha, a line of copper, which is immediately 8 kilo electron volts, and which is very near the high X-ray regime. So in fact, you already can put your sample in air. You don't even need vacuum for that. Yeah, so that's the way. So the advantages, you can immediately go to much higher energies. The disadvantage is that you lose this spatial coherence property. Thank you for the question. So can we progress the same way?
Yeah.
There's more about the quantum nature at the back, which I didn't dare to show.
One more question. Beware, the answer can be long.
Would be nice if young people ask.
Next time. Okay, so if there are no more questions right now, so let's thank the speaker again.
Thank you.
And besides applauses, we have some presents for you, one from the organizers.